Hello, this is Gabriel Palmer, and I'm going to be talking today for Connix, doing a deep dive into nanoprocesses. I'm going to be talking about them as an abstraction for secure, portable, and computation for many different things, including IoT, AR, and the edge. I'm Gabriel Palmer. I work at the George Washington University. And I want to dive in by talking about the fog. So the fog is this general notion spanning between the cloud, the edge, and the actual devices. We see on the right a lot of devices connecting to, in this case, the edge cloud. This includes AR and mobile, connected vehicles, different IoT devices with different properties, and a lot of imaging systems that are sending video up to the cloud eventually. Now, on the right here, these are traditionally relatively latency sensitive computing platforms in many ways. AR and mobile, for instance, with the tactile internet and with augmented reality, require responses very quickly to be able to display for the user. IoT devices, especially when they want to coordinate over the network, need to coordinate within reasonable amounts of time, etc. Now, the problem is that the cloud, the traditional cloud, has a relatively long round trip time between 20 and 50 milliseconds, and because it's over the wide area network, it's not very predictable. One of the main benefits of the edge that we're going to emphasize is its relatively predictable round trip time of around 1 milliseconds for 5G. Current 5G deployments are closer to 10 milliseconds, it seems, but the technology should be able to scale down to that. So the edge is a very valuable commodity when you start thinking about all these IoT devices coordinating with each other and with a broader system, because it has a latency with which they can get replies within an amount of time that's useful to them, so that they can respond to the user or to each other. The problem with the edge is that there are limited resources at the edge deployments, which may number in, the hundreds of thousands across the United States. So we can't have these deployments be as large as traditional data centers. They're going to span between, one system and a few racks of systems, for instance. This raises a number of problems. One of them is that we need to worry about security, of course. When we have all of these computations running in the cloud and running on our devices, all communicating to each other over the internet, security is always paramount, and a lot of systems don't necessarily treat it as such. We would like to think about our systems as taking security as a first-class concern. Especially when talking about the edge, but also when talking about some of the devices, programming them always is going to have limited resources. At the edge, we particularly care about high density. We want to be able to pack a lot of tenants' computations onto the limited resources that exist at the edge. And fundamentally, all of these systems should be designed with some notion towards latency sensitivity. The hypothesis that we're going to be working on throughout this talk is simply that the best to meet these challenges, these goals, would be best approached with a programming model that considers distribution, security, and timeliness as part of the model. And this is the framing that we're going to use to discuss nanoprocesses. And nanoprocesses are a very vague thing, and definitely if you talk to two different people, they'll probably say different things. They're very related in some sense to component-based systems, but how I'm going to define nanoprocesses here is relatively vague, but also oddly specific in some ways, and that's that they are a lightweight computation abstraction. On the right, you see the execution context, or the thread associated with it. They also have a protection context, or as you'd traditionally draw for a process, the oval surrounding the thread. The protection context here is really important because it means that we cannot actually impact what is outside of that process abstraction. There's some notion of isolation, except for through the explicit interdependencies as shown in the purple. And these are interfaces that we can use to programmatically and functionally interact with the surrounding system, be that other nanoprocesses or be that a different part of the system. And one of the dominant parts of a lot of nanoprocess systems is that they do all of this with a sub-process granularity. Here, process, I mean something like a POSIX process created with fork. You could have many different nanoprocesses running within one of these larger processes. So that gives you a sense that these are a kind of nano abstraction, focusing on being smaller, having stronger isolation, and less resource usage. One of the important parts of nanoprocesses is that they don't come with all the baggage of normal Unix processes. They don't have file descriptor tables, they don't have all of the kernel state associated with them. They are simply the protection and execution context and then the interdependencies that might add on some of those resources, but not necessarily. So we think about an application when we think about nanoprocesses as not necessarily a single nanoprocess, but a collection of nanoprocesses that coordinate in controlled ways to express the functionality of the application. Additionally, we have to have something that controls and provides these abstractions, which for the sake of this talk, we'll call a monitor. And that might be executing within the overall process that runs the many nanoprocesses within it. It instantiates them, it provides them system abstractions, things like memory allocation, etc. It might provide networking and I/O, might provide storage and persistent, it might even provide system-specific abstractions for very small IoT systems. So the monitor can be widely variant in many different ways. Now, we're going to focus on security in many different ways, and nanoprocesses help us with that. So they allow us to not only sandbox the execution within the nanoprocess, but it allows us to do things like control the communication between that sandbox and other parts of the system. This limits the memory access and control flow throughout the system, allowing us to implement fine-grained access control, dynamic information flow control, stuff like this. Now, to explain how nanoprocesses can be relevant for existing systems, I think it would be useful to demonstrate or to talk about how existing systems have kind of focused on a few different problems. So the first is how systems that we've had have created an abstraction for applications. So we started out with Unix processes, but these didn't really scale very far. We had a lot of complexity that was introduced into the system because we had a ton of DLLs that a Unix process needed to have, and certain files within their file system image that were required in specific ways. They required things like databases, they required external daemons. Our applications became relatively complex. And if you remember the old days in the early 2000s of DLL hell, we had a lot of problems with this. So what we really needed was an abstraction for an application. And we got this when we got self-contained virtual machines in the early 2000s when they started to take off, and especially in the mid-2000s when the cloud started becoming prominent. A VM was a convenient abstraction for an entire application because it wrapped up all of the dependencies. It also conveniently provided multi-tenancy, which were required in the cloud. But we found out that VMs are not the lightest weight abstraction, and often we just want an application abstraction, and containers tend to do this relatively well. They have less isolation than virtual machines because you rely on the same code base. The trusted computing base is exceedingly large, but for all intents and purposes, they provide this application abstraction quite well. Modern systems are kind of going into a more nuanced approach where we're using virtual machines for different tenants. Here you see T0 and T1. And we make kind of the isolation properties of the system reflect the security relationships in the system. So we have these two tenants. Within them, we might run containers to be able to run the applications of the tenants. Now, the goals that we have as we kind of have gone throughout history and kind of found these different abstractions is that we always need strong security for multi-tenancy. We often increasingly want strong isolation for libraries, but none of these abstractions have been ideal for that. We want high density, which is often what continues to motivate containers, but of course security often brings us back to VMs. And we want this notion that an application is the application plus all of the dependencies. And I would claim that nanoprocesses can provide a lot of this. Here we see a very small number of nanoprocesses, some of which run libraries, some of which have different parts of the file system. And we have two tenants represented as different nanoprocesses. The tenants have the inner tenant isolation required because they're being run in different nanoprocesses. And we can control the relationships between these by, for instance, here allowing T0 and T1 to access the same programmatic file system image from within another nanoprocess. We can also, as seen here, isolate out the library from T0 if it is less trusted or more important. And we can see at the bottom we have a monitor that can provide whatever abstractions are required. Here, for instance, maybe a file system to a subset of the nanoprocesses that could be specific for the certain application that is being run. But the monitor is extensible because it's implemented in user-level code in a process, for instance. We might extend it to, for instance, also provide pub-sub style communication between nanoprocesses, right? So this enables us as system designers a lot of flexibility. So nanoprocesses provide a very interesting example here of something that might solve a lot of the historical problems for an application abstraction that we require. Additionally, if we look at the evolution of embedded software, we see the same problems coming from a different side. Here we see a very, very traditional embedded system design where we have a real-time operating system being paired with domain-specific software that often is certified, that's very expensive and a long process, and put onto the embedded device. But about, 10 years back, 15 years back, we started requiring mixed criticality systems, whereby we simply needed more complicated systems and therefore needed to use less assured system like open source software and third-party software. Or we needed to consolidate a lot of software onto a smaller number of embedded systems to save cost. So we also saw these systems being connected to the internet increasingly, which of course makes security a fundamental concern. IoT has added another level of complexity to that because we no longer can do certification when we're talking about cheap commodity systems, but they are still connected to the internet, which is a prevalent part of the idea of IoT. So what we often want in these systems is strong security, assurance-aware isolation, and we want whatever we do within the system to be lightweight and predictable because they're extremely constrained resources. I would say that nanoprocesses are a good fit for this as well. Whereas a lot of embedded systems have simply never adopted security as a fundamental abstraction, nanoprocesses can provide that. So now we can have multiple isolated nanoprocesses speaking to each other in only controlled ways, and talking to a monitor that might provide abstractions for interrupt handlers and whatnot for them to interact. The monitor also might provide transparent communication between nanoprocesses that are spread over the internet. So we have stronger isolation. Because we can control the monitor, we can attempt to provide real-time and predictable behavior. And this becomes a foundation on which we might be able to add a lot of security and isolation to these types of systems. So nanoprocesses are fundamentally an interesting idea that might span to many different domains. The question is, can they be real, right? And right now we have a few examples of nanoprocesses in the wild. One is those implemented with Webassembly. And Webassembly is a popular standard now. It provides sandboxing through software fault isolation paired with control flow integrity mechanisms so that whatever basically is happening within a sandbox cannot impact the stuff outside. It's a very, very simple memory model. You really thinks of all of the memory within the sandbox as just being a linear array, as opposed to things like the Java VM that have a defined object model. This is interesting because it makes WebAssembly a thin waist between languages and architectures. Many different languages can be implemented in WebAssembly, including C and C++ that require this linear notion of memory. And WebAssembly is portable, so it can be implemented on many concrete architectures. WebAssembly is popular. It's used in Fastlane Cloudflare for client computations on the edge. There are serverless runtimes, including our own Sledge for doing this. Browsers can all run WebAssembly instead of JavaScript, and browsers use WebAssembly due to some of the initiatives within Connix for library isolation. So less trusted libraries can run in WebAssembly instead of potentially being compromised and compromising the entire browser. And it can also run on very small systems, including IoT devices. So WebAssembly has been shown to provide nanoprocess with sandbox security, typed interfaces for composition so that you can create applications out of many different WebAssembly sandboxes. It's multilingual and portable. So this is really compelling. But nanoprocesses have also seen a resurgence in research over the past decade on the hardware side. We have component-based systems that I'm going to very broadly define as those that are using some of the hardware techniques for isolating these different nanoprocesses. These include things like fat pointers within Cherry or the ARM Morello initiatives that is adopting Cherry into ARM. This needs to be extended with a notion like object capabilities like the Cherry people did so that you can have the sets of accessible capabilities switched in a atomic manner to be able to provide switches between different nanoprocesses. A lot of these, there are also additional techniques that provide kernel bypass IPC through call gates. Things like memory protection keys, Intel memory protection keys allow us to have a notion of nanoprocesses that don't even need to switch to the kernel to switch between them. And TrustZone M actually has a very related notion for switching between worlds that is implemented in a similar but different way that's very compelling. And generally, microkernel IPC can be seen as a way to provide nanoprocesses. The properties of these systems are quite appealing. Because they're done in hardware, normal code is executing within the nanoprocess, so there's no slowdown. So IPC, but the downside, of course, is that IPC requires hardware interaction. So we need to switch between protection domains in some way, and this implies some overhead. So a lot of research is around there. How can the hardware minimize these overheads for switching between the nanoprocesses? This is used in a lot of research runtimes. It's used in unikernels. It's used in a lot of kernel bypass techniques, a lot of systems that use DPDK. And it's generally something that I hope is getting a lot more attention. Because a lot of these systems are based on capability-based systems, the security for inner nanoprocess communication and coordination is often capability-based, which is a strength. Because a lot of the protection is provided by hardware, you often have a very small TCB within software for these systems, which aids us being able to say that they're trustworthy. And the downside is, of course, that they really require a careful interplay between hardware and software to work. Now I want to give a few notions of where we've used nanoprocesses in the past. Here we have a system on the left. You see devices interacting with the edge, and you see this massive collection of things executing on the edge. This is called EdgeOS, and it used a notion of hardware-protected nanoprocesses for processing packets as they went through the system. This was used to isolate different clients. So every single client had a collection of featherweight processes, as they were called, these nanoprocesses processing for them. So this was a highly secure, fast nanoprocess system for network function virtualization. And it allowed us to customize the monitor within the system, to use DPDK, and to use very fast abstractions because we had this nanoprocess abstraction. And what it enabled us to do was have line rate processing while having strong isolation with per client nanoprocesses that had 4x higher memcache throughput than Linux-based systems and up to 100 times lower tail latency. Another example is on the WebAssembly side with our Sledge runtime. And this was very similar. It was focused on the edge, and we had the single process runtime running on Linux, where we essentially did kernel bypass for many aspects of what you'd want to do within the serverless system. We used WebAssembly-based nanoprocesses for the isolation, therefore not needing to use processes with Linux that are generally quite heavier weight. We used our own awesome compiler for WebAssembly for that, so they were fast. And we were able to customize the monitor monitor to be able to provide fast instantiation of nanoprocesses, workload distribution in a way that was serverless aware, and a whole bunch of other optimizations. And we also were able to build on top of Linux, which of course has the benefit that we didn't need to implement everything like in EdgeOS. So Nanoprocesses here enables specialized serverless runtime for the edge. We had 50 microsecond startup of Nanoprocesses, which is orders of magnitude faster than a lot of the competitors, that enabled up to 3x higher throughput than Linux with 4x lower 99th percentile latency. Last, we showed that nanoprocesses can be used on microcontrollers. These are in some ways the most adversarial embedded systems because they have very, very small amounts of memory in the tens or hundreds of kilobytes of SRAM. And here we investigated embedded WebAssembly, eWasm, that was a runtime paired with a compiler that specialized for these small little systems. So it provided sandboxes on these systems that often provide no isolation whatsoever and had only a 40% slowdown versus C. They also had on the order of a 10 times faster or smaller properties than things like JavaScript or Python that are actually pretty common on IoT devices, often with a fixed memory overhead. What we did notice is that it's hard to have benefits in all dimensions. Sometimes to get faster, you require more memory, etc. So there's a lot of work to be done here. Now, I want to summarize all of this by just addressing some of the things that Connex is doing and some of the big areas where there's work to be done. We need to do work in distribution as a large research community, figuring out how different parts of an application map to which parts of a system. We need to figure out how applications specified as the compositions of nanoprocesses can be loaded onto systems efficiently and run effectively. And we need to build runtimes that can manage the end-to-end latency required by the dynamics between edge and devices. We also need to make security constraints, i.e. for multi-tenancy, kind of a fundamental abstraction within the system. Within WebAssembly, there are a lot of things that need to be done. We need to customize the runtime environments by providing kernel bypass where possible, and hopefully customizing to specific types of hardware. We need to make the entire system trustworthy. And Parno and Stefan are all looking at verifying the resulting code to verify that the sandboxes have integrity. We need to look at things like how we can minimize execution overheads within these systems, and I think there's a lot of promise in combining the WebAssembly abstraction with things like hardware abstractions for CFI and bounds checking. One of the challenging areas is data movement between sandboxes. How can we actually pass data while maintaining protection between sandboxes while avoiding copying? We also need to be able to talk between languages, since different languages can be in different nanoprocesses. This becomes like a lot of engineering work, but a lot of very important engineering work. And we need to define what the operating system can provide. Reliability is a big opportunity here as well, because we have direct access to all of the memory within the sandbox, so checkpointing and other reliability techniques are a big deal. On the hardware side, we have very similar things. At the runtime, we need to do things like revisiting microkernel design, providing lightweight VMs or whatnot to provide a useful and strong sandboxed environment for nanoprocesses. We need to figure out how we can make these things as fast as possible by minimizing context switch. MPK goes a long way in this direction, but it's not necessarily sufficient because it's very hard to also provide CFI and other properties with MPK. Cherry object capabilities go a long way, but revocation becomes the difficult operation to perform. So when we're interacting and we want to move data, there's a lot of potential there, but it's not clear whether we have a silver bullet for solving it yet. And we need to, similar to WebAssembly, define what the operating system should look like for this. POSIX is probably not the answer. So in short, nanoprocesses are interesting. They are a compelling direction to go. and they solve a lot of problems. They provide us an application abstraction. They provide strong security even when we scale down to microcontrollers. They can, depending on the technology, for instance, WebAssembly, provide portability and the ability to perform distribution. And they enable a lot of specialized runtime so that we can, for instance, provide latency sensitivity in our edge-based systems. However, there's a lot of work to be done. So I'm glad to talk about this. If you have any questions or comments, please ask questions here. Thank you very much. Appreciate it.